section 1.6 or 5.6, depending on whether you're looking at Calculus 1, Calculus Volume 1 or Calculus Volume 2. These are all integrals involving exponential and logarithmic functions. To begin with, we have, of course, our rules. The integral of e to the x dx equals e to the x plus c. Of course, we have plus c because these are general antiderivatives. And just like before, the derivative of e to the x is e to the x. The integral of e to the x is also e to the x. So it is one of the most beautiful functions you can have. Now, our second type of function here is also an exponential, but it is with a generic base. Okay, we have a to the x, not e to the x. Okay, not a particular one. Okay, any of them, we can do a to the x divided by natural log of a plus c. So in a sense, we have to scale back by a factor of that a. All right, so that would work, by the way, if it was e. If it was a base e, it would just be ln of e is 1 because it's its own inverse. All right, so let's just dive into some antiderivatives here. So example 1 is e to the negative x. If it were e to the x, it would be boring. Okay, so first let's define u to be our exponent negative x. Well, that means that du is going to be negative dx, negative 1 dx. Okay, now what we're trying to do with u substitution is replace everything in this expression here. So this would make this integral e to the u, but we can't exactly replace the dx. So what we need to do is rearrange this. This means that negative du is dx. So we'll replace dx with negative du. We'll go ahead and factor up a negative outside of our integral. So e to the u, the integral of that is just e to the u plus c, based on our first rule. Now I'll go ahead and throw that negative factor in there again. Now because u is negative x, we'll replace this back in there. Negative e to the negative x plus c. Now we can check this by taking the derivative of what we have right here. And if we take the derivative, we will get, based on the chain rule, a positive e to the negative x, which is what we started with. So that in fact does work. Remember, we can always take the derivative of our answers to see if that matches our integrand from above. All right, number 2. The easy choice for u here is still negative 2x cubed. So the derivative of that, du, is negative 6x squared dx. Don't forget that. Now we're actually trying to replace an x squared, so we will rearrange this by dividing by negative 6 to be negative 1/6 du equals x squared dx. What that means is when we replace this, we rewrite this integral, we are going to have negative 1/6 du, so we'll have a du in here, and we are replacing e to the negative 2x cubed with e to the u. Alright, so that, the integral of that is negative 1/6 e to the u plus c. And if we replace the u back, reverse our u substitution, negative 1/6 e to the negative 2x cubed plus c. And that's it. Alright. We still have a fairly obvious choice for example 3. We can replace the 1 plus e to the x, mostly because we can take the derivative of that very easily, and that is just e to the x. Derivative of a constant is 0. E to the x dx. Alright, so du actually replaces both of these. So this is the integral of u, and it's the square root of u du. Now I am going to rewrite this as u to the 1/2, because then I can use my power rule. Alright, so that would be u to the 3/2 divided by 3/2 plus c. I'm going to rewrite this a couple of times. Okay, first I'm going to write this as 2/3 u to the 3 over 2. And then last, I'm going to replace my u. So this is 2/3. U is 1 plus e to the x to the 3 over 2 plus c. We'll continue to use u substitution on number 4. My u is again going to be what's inside this parenthesis. It's the inside function there. So that is going to be 3 e to the x minus 2, which makes my du 3 e to the x. The derivative of the negative 2 is just 0. Right. Now we need an e to the x out here, e to the x dx. So we'll move the factor of 3 and make that 1/3 du equals e to the x dx. Alright, so we can rewrite this as 1/3 du, and that will be u squared, because the du includes the e to the x and the dx. So this would be u cubed over 3. Now we can't forget our factor of 1/3. Alright, so that would be u cubed over 9 plus c, which, because of our u, is 3 e to the x minus 2 cubed. And I'll go ahead and write this as 1/9 plus c. All right, number 5. Our choice for u, because e to the u is integrable very easily, okay, often we want to replace the exponent on it to make it just an e to the x or an e to the u or e to the t or something like that. So that's why we keep replacing. I've replaced several times with that. However, if you notice on number 4, or for that matter, on number 3, we already had e to the x. We didn't need to replace an exponent. So replacing the term in here, the terms right there, making that a u made this easier because it turned it into something that is like a polynomial. We could use our power rule on. Whereas here we have an inside function, something that is being squared, so that becomes the easiest thing to do. Whereas here we used the exponent as u, the exponent as u. All right, so on a lot of these, if we can replace the exponent, that often makes things a little bit easier. So this one I'm going to use 2x cubed. And so that makes du, the derivative of that is 6x squared. Now if you notice here, I need a 3x squared. 3x squared dx. I have a 6x squared dx. So what I'll go ahead and do is divide by 2 to make this 1/2 du. And that's 3x squared dx. That's what I wanted. So we'll go ahead and do that. So this integral becomes 1/2 du. Du includes the 3x squared and the dx, so we just are left with e to the u. And the integral of this, the antiderivative, is e to the u, so 1/2 e to the u plus c. And then once we replace u, that's 2x cubed plus c, that integral is complete. Alright, moving on. Number 6, find the price-demand equation for a particular brand of toothpaste at a supermarket chain when the demand is 50 tubes per week at $2.35 per tube, given that the marginal price-demand function, p prime of x, for x number of tubes per week is given as p prime of x equals negative 0.015 e to the negative 0.01x. If the supermarket chain sells 100 tubes per week, what price should it set? Okay, so the first thing we should do is identify the information we have. We have some information that actually goes together. These two right here, 50 tubes per week at $2.35 per tube. That would be the ordered pair, 50, comma, 2.35. Alright, where x is the number of tubes and p is the price. That's actually going to help us find the constant of integration, okay, the c at the end of this particular question. Now, we're actually being asked to find p of x. We want the equation for price and demand, that it's x and p of x, but that we're given p prime of x. So what we're going to have to do here is to find p of x. That is going to be the integral of p prime of x dx based on the fundamental theorem of calculus, part 1. Okay, we can replace this. And so that would be the integral of negative 0.015 e to the 0.01x dx. Notice the variable of integration, I'm using dx there because my function is in terms of x. All right, now the integral of that will be, we're going to have to use u substitution. So u is, I'm going to go ahead and use negative 0.01x. So that du is negative 0.01 dx. If you notice, we have a number out here, negative 0.015, a constant there. Now, what we need to do, though, is we need to adjust this to make sure that we have this. So what we could do if we didn't know what number to do, we could divide by negative 0.01 and then multiply by negative 0.015. I do happen to know, however, that if I multiply both sides here by, I'll just go ahead and do that, by, 1.5, that will get me the constant that I want. Let me just double check that. 1.5 times 0.01, negative 0.01, that is negative 0.015. So that would be negative 0.015 dx is 1.5 du. So we'll go ahead and use that. That'll be 1.5 du, and I'm going to go ahead and factor that constant out of my integral. Alright, so 1.5 du, that takes care of the 0.015 and the dx. Now that will be e to the u, and so this is a very familiar integral at this point, hopefully. That means we get 1.5 e to the, I'm going to go ahead and substitute my u back in, negative 0.01 x, and that is plus c. So that is p of x. Okay. Now we need to use this point we're given, 50, 2.35, to determine what c is. So if my price is $2.35, okay, that is 1.5 e to the negative 0.01 times 50 plus c. All right. Well, if I calculate that first part, 1.5, and then plug that in there, that is going to be 1.44, I believe is what I have here. Let me do that again just to make sure. E to the negative 0.01 times 50. Okay. Yep, so that would be 0.909795. And then we subtract that, 235 minus that answer. We get that c equals 1.44. Alright, so that means that my equation for the price is, in fact, p of x equals 1.5 e to the negative 0.01 x plus 1.44. Now what we're actually asked for here is if they sell 100 tubes per week, what price? We actually are trying to find price. So the price, if they do 100 tubes per week, it's 1.5 times e to the 0.01 times 100 plus 1.44. And so our price at 100 tubes is $1.99. Is that right? That doesn't seem right. I did this earlier, but I'll do it again. 0.01 times 100 plus $1.44. That is $1.99. Okay, that works. Which is what we were after here. And of course, the point of a video is that you can go backwards and forwards and rewatch things. So hopefully you've paused this if I was going too fast or anything. All right, number 7. Suppose the rate of growth of bacteria in a petri dish is given by Q of t equals 3 to the t, where t is given in hours, and Q of t is given in thousands of bacteria per hour. If a culture starts with 10,000 bacteria, find a function Q of t that gives the number of bacteria at any time t. How many bacteria are in the dish after 2 hours? All right, so in the end, what we're actually trying to find is cap Q of t equals something, and in particular, we really want to know the amount after 2 hours. That's what we're really after. All right, so cap Q of t is equal to the integral of lowercase q prime of t, or just q, actually, because Q of t is the rate of growth. So in effect, this is q prime of t. That's what that is. So if we integrate that, that will give us the cap Q of t, which tells the number of bacteria. All right, well, that means we are going to have the integral of 3 to the t dt. Now, based on our formula, I say our formula, the equation we had at the beginning was the integral of a to the x is a to the x divided by a natural log of a plus c. So the integral of this is 3 to the t, over natural log of 3 plus c. That is what Q of t is. Now, to find c, we're given that it starts with 10,000 bacteria. That is a point. This right here is a point. 0, 10,000. So we can plug this in. 10,000 equals 3 to the 0 over natural log 3 plus c. So if we solve that equation there for c, c is 9,999.09. And I wouldn't round it to 2 decimal places. All right. So this gives us the equation Q of t equals 3 to the t over natural log of 3 plus 9,999.09. All right. To actually find the answer to our question, we can plug 2 in. So that would be 3 squared over natural log 3 plus 9,999.09, which gives us that Q of t is approximately, because this is not going to be exact, over natural log 3 plus 9,999.09 is 10,007.28. So I'm going to go ahead and say it's approximately 10,007. That's how many there will be after 2 hours. All right, last one of these that we're going to have that explicitly uses exponentials. Evaluate the differential in the definite integral using substitution. So from 1 to 2 of e to the 1 over x divided by x squared. Now I said previously we want to try to make the exponent either a single variable, right? A u, a t, an x, something like that. So even though this looks fairly complicated, it's really not. Okay, we can make u 1 over x, which would make an e to the u over there. Now, that means that du is negative 1 over x squared dx. Now, that hopefully looks a little familiar because we have it divided by x squared over here. Right? So I'm going to go ahead and rewrite this, okay, as 1 over x squared times e to the 1 over x. I mean, that's what it is. So to get the 1 over x squared there, I need to move my negative sign. So that would be negative du, differ it by a constant, 1 over x squared dx. Now, when I go to replace this, it is going to be the 1 over x squared dx is taken up by negative du, and it becomes e to the u. Now I'm going to go ahead and change my variable. Okay, Okay, so I started with x's. I'm going to convert these to u's. Upper limit is 2, lower is 1. Since it's 1 over x, my u becomes 1/2 and 1. So I'm integrating from 1 to 1/2. Next thing I'm going to do is actually put these in order because we have some properties of integrals, and that is we can convert this to the integral from 1/2 to 1, change it to positive from negative, and that is e to the u du, which makes this e to the u evaluated from 1/2 to 1. So this will be e to the 1 minus e to the 1/2, which this is going to be approximately 1.0696. That's the approximate value of that integral. Okay, that's all we're going to have for exponentials. The next thing we need to look at is logarithmic integration. Logarithmic integration. Alright, so we have a couple of rules here. The first is the integral of 1 over x dx is the natural log of the absolute value of x plus c. Alright, we're going to use that one quite a bit. And we'll use u substitution like the others to try to get it to look a little better. Alright, now we have the integral of natural log of x dx is x log x, natural log x, minus x plus c. And the last one we have is the natural log, well, if we don't have a natural log, if we have a log in some other base, log base a of x dx, the integral of that is x over natural log a times natural log x minus 1 plus c. Alright, so let's work with number 9. Find the antiderivative of the function 3 over x minus 10. Alright, so this is the same as us saying we want the integral of 3 over x minus 10 dx. It's assumed that we're going to use x for this because that's the variable our expression's in. Alright, well, let's use u substitution. Try to get it to look like one of those. I bet we're going to look like 1 over x, what we want it to be. So u is x minus 10, which makes du 1 dx. Alright, so let's go ahead and I'm going to factor the 3, that constant, out of here, and make it 1 over u du. Alright, well, from our equation right up there, that is 3 natural log of the absolute value of u plus c. And because u here is x minus 10, that is 3 natural log of x minus 10 plus c. Okay. Now let's try number 10. We've got the antiderivative of 9 over 3x plus 5 dx. Same idea, we're going to use u equal to 3x plus 5, which makes du 3 dx. Now I really need to replace just the dx, so I'm going to write this as 1/3 du equals dx. Alright, so when I integrate this, first I'm going to bring that 9 out. 1 over u du. Now, that's not quite going to work because I have that 1/3 there. Let me bring that 1/3 out. Alright, so I need to multiply 9 that I factored out times the 1/3. So that will be 3 natural log absolute value of u plus c, which will be 3 natural log of 3x plus 5 plus c. Alright, number 11 looks a lot more complicated. It really isn't that crazy because we want this to look like 1 over x, right? Well, if I make my u equal to, I'll go ahead and rewrite this, 2x cubed plus 3x over x to the fourth plus 3x squared. Okay. The wise idea here would be to make u equal to x to the fourth plus 3x squared. The reasoning there is that when I take the derivative of that, I might get something with a couple of lower exponents, which is what I happen to have in my numerator. So oftentimes when you see something like this, making the denominator equal to u, if you take the derivative and it becomes something that looks like your numerator, that's a good idea. Okay, that helps. So this would be 4x cubed plus 6x dx. Now, that does not look like what I have in my numerator. However, it differs by a factor of 2. So if I divide everything by 2 here, or in essence, make this 1/2 du, that is 2x cubed plus 3x dx, which is what I want. So this will turn into the integral 1 over 2 du, and that would be 1 over u. So I have 1/2 natural log of u, x to the fourth plus 3x squared plus c. That's really all there is to that. Even though it looks pretty crazy, that's all there is to it. Alright. Find the antiderivative of the function log base 3 of x. So log base 3x dx. Now we had a formula, right? I guess that's what you would call it, a formula at the top of our paper there, that's log base ax equals log base ax, the integral of that, dx, equals x over natural log a times natural log of x minus 1 plus c. Now we can use that with this. The difference is our a, in this case, is just 3. Alright, so a is 3 in that function. So this would be x over natural log 3 times natural log x minus 1 plus c. We did not have to use u substitution, so we can keep the x where it is. That's it. Last one on this. Integral from 0 to pi over 2 of sine x over 1 plus cosine x dx, and this is the definite integral. So we should get a number answer here. Alright, now what I said earlier still holds. If you look and you see something that you could take the derivative of to get something else, alright, that's usually a good idea. So the derivative of sine is cosine, but we really don't need a 1 plus cosine there. But if these two have a relationship like this in a fraction, where the derivative is on top or the derivative is on bottom, and vice versa, the other's in the denominator, numerator, then that's where the natural log comes in. So let's try u equal to 1 plus cosine x. Well, then du is negative sine x dx. Well, if you notice, we have a sine x dx right here. So we can make this negative du equals sine x dx. So we'll replace sine x dx with negative du. So negative, which I can factor out actually, negative du. The sine is taken up with that negative du, so we have 1 over u. Now, the limits of integration, though, these are going to change because we're going from x's to u's, beginning with pi over 2 and 0. All right. Cosine, 1 plus cosine of pi over 2 is 1. I'm going to do that again. I did that earlier. Cosine pi over 2 is 1. And 1 plus cosine of 0 is 2. So this changes to integrate variables of integration from negative. We have 0 to 2. I guess I didn't need to do that. So from 0 to 2, or from 2 to 1, 2 to 1. All right. Now I'm going to change this to from 1 to 2 of 1 over u du. So this would equal the natural log of the absolute value of u. I'm going to go ahead and replace this as 1 plus cosine x. Okay, and we're evaluating this from 1 to 2. Now if I plug 2 in, oh, you know what? Don't do that. Don't do that. This would be the natural log of u evaluated from 1 to 2. I changed my limits, so I don't need to do that. So this would be the natural log of 2 minus the natural log of 1, which is the natural log of 2. And since those are both positive, the absolute value bars do nothing for us. Okay, so that is the end of section 1.6 or 5.6, depending on what you're looking at, over exponentials and logarithmic functions.